Okay, it's time to learn about sequences. A sequence is just an infinite list of numbers. Here's a really famous one. It's called the Fibonacci sequence. It's the numbers 1, 1, 2, 3, 5, 8, and so on. It just keeps going. More generally, we might talk about sequences in a kind of general notation by using numbers for the subscripts. So S1 means the first element in this list of numbers, S2 means the second, Sn means the nth, and so on. Now, to get a little bit more concrete, there are a lot of different ways we could define a sequence. One is we could just write down the list as we did before. You know, we could write down 1, 1/2, 1/4, 1/8, and so on. That's a sequence. And of course, that sequence might be generated by some rule that it might be your job to figure out. Another way we could define a sequence is by giving that rule. So we could give kind of a function-like formula that says, the nth element of the sequence is 2n plus 1 over n, where n starts at 1. And if we plug in 1, we get the number 3 over 1, so that's 3. If we plug in 2, we get 2 times 2 plus 1 over 2, that's 5/2, and so on. Another kind of rule you can use to define a sequence is a recurrence relation. And that tells you the nth element in terms of some previous elements. So here's an example. It's the nth element is equal to the sum of the previous two elements, and I'm going to tell you that the first element and the second element both are equal to 1. And you have to know that in order to generate things from there forward. So a 3 would be the sum of 1 and 1, that's 2. A 4 would be the sum of a 2 and a 3, so that's 1 plus 2 equals 3. A 5 would be the sum of a 4 and a 3. That's 3 plus 2 equals 5, and so on. So we have the list 1, 1, 2, 3, 5, and so on. And that's that same Fibonacci sequence that I mentioned above. By the way, that's a really cool one that I really like. It pops up a lot in math, and it turns out to be related to lots of things in nature, too. Now, when we talk about sequences, a common question we might ask is about convergence of the sequence. And what we say is that a sequence converges if it settles down to a fixed finite value as we keep going out further on in the list. And more technically, this is a limit. And the way we write this, in case you haven't seen limits before, is the limit as n goes to infinity of a sub n. That means you imagine going far, far out in the list and asking what happens to the nth term. And if it equals L, where L is some finite number, then we say we have convergence. If we don't have convergence, we have divergence. So here are a few examples. If we have minus 1 to the n, it flip-flops. It never settles down to a particular value, so that diverges. If we have n squared, well, 1, 4, 9, 25, kind of keeps growing, never settles down to a finite value, that diverges. Here's another one. N squared plus 1 over 2n squared minus 5. Well, maybe it's not so clear. So let's think about what happens when n gets really big. And when n is big, n squared is much more important than 1. And 2n squared is much more important than this minus 5. So the limit as n goes to infinity of this expression is equal to the limit as n goes to infinity, and we just retain the highest degree terms. So that's n squared over 2n squared. The n squares cancel out, and we get 1 over 2, or 1/2. So it will settle down to a particular value, and so we say it converges. And if you're not happy with this algebra, you'll hopefully get there in time. Also, making a graph using a program like Mathematica can be really helpful. Are there other ways we can show convergence? Well, the notion of bounding is useful. Bounding a sequence just means finding numbers that the sequence is in between, and that could be inclusive. So to give you an example, the sequence 1, minus 1/2, 1/4, minus 1/8, and so on is bounded between 1 and minus 1/2. Of course, it's also bounded between 30 and negative 50, right? There's many other bounds possible, which gave you one example set here. And the reason I'm telling you about bounding is that there's a theorem that says if a sequence is bounded and monotone, it converges. And what monotone means is just goes in one direction, like it's always decreasing or it's always increasing. So to give you an example, 1, 1/2, 1/4, 1/8, You could probably solve that as a limit problem as well to show that it converges, but let's just say, is this monotone? Yes, because it keeps decreasing. Is it bounded? Yes, because we should be able to argue that 0 is always smaller than this and 1 is at the upper end. So since it's monotone and bounded, it converges. Now, use your mathematical logic skills here. Just be aware that the converse doesn't have to be true. You can have convergent sequences that are not monotone, right? So just because it's not monotone doesn't mean it's not convergent. However, you can't have convergent sequences that are not bounded. So any convergent sequence is going to be bounded. If you have a sequence that's unbounded, it's definitely not convergent. All right, thanks for listening.